as R and theta. We not replace Z because Z is in 3D space. So our coordinate system will be based on R, theta and Z. Based on the picture, remember R is going to be our distance out in the plane from origin, and theta is not in the typical XY plane, which is measured the counterclockwise or clockwise, and of course Z is going to be our height, and it's positive when above the XY plane, and it's negative will be below XY plane. Next is volume. The triple integrals for rectangular coordinate is given by dv, dx, dy and dz. Or we can order it as dz, dy or dx and in difference order. So now we want to replace dx, dy, dz to cylindrical coordinate, which is r, dr, theta, dz. So in this video, we're going to do this order dz, dr, d theta. So we prefer to do our z component is our triple integral. So this is the question that we choose in triple integral in cylindrical coordinates. So the question is, when constructing a building, an engineer estimate the amount of energy which is work to lift a metal rod from sea level, which is Z equals to 0. Consider a metal rod having a uniform height of 10 meter above Z equals to 0 and extending in Y direction by diameter 3 meter. Assume the metal rod is bounded by Z equals to square root 100 minus x square minus y square, and x square plus y square equals to 9 and Z equals to 0. The weight density of the material is 15 kg meter per second square. Assume the metal rod is lifted from the sea level to height 5 meter. The total work Q required in constructing the building is computed as triple integral as given by Q equals to triple integral 15 kg meter per second square times 5 meter dv. So hence calculate the amount of energy work which is Q.
From the equation given in the question, we have Q equals to triple integral 75 r dz dr d theta. Instead of using dy dx, we use r dr d theta because our R region is a circle. Then for the limit, we must look at the graph. For the z limit, we have 0 here until z equals to square root 100 minus x square minus y square. But because of we use dr d theta instead of dy dx, we must substitute x square minus y square into r terms. So we have square root 100 minus r square. And then for the r limit, we have 0 until 3 because our R region is a circle which have the radius 0 until 3. And then for the theta, we have 0 until 2 pi because our R is a full circle. Then firstly, we must integrate by turn from dz, dr and then d theta. For integration of z, we have 75 rz from 0 until square root 100 minus r square, and then we substitute the limit. We have this equation. To integrate r, we must use u substitution. So we let u equals to 100 minus r squared, and then we differentiate the u in terms of r. We get du dr equals to negative 2r, and then dr equals to negative 1 over 2r du. Then we must substitute the u terms into the r, and then our equation will become like this: negative 75 over 2 square root u du d theta. And then we integrate the u, we get negative 25u power of 3 over 2. The limit is from 0 until 3. But because of the limit is for the r, we must substitute back the u. We must substitute back the r into the u. So we will have this equation: negative 25, 100 minus r squared power of 3 over 2 from 0 to 3. Then only we can substitute this limit. And then we will get this equation. Then we substitute the theta, we will get 3297.88 theta. And the limit is from 0 until 2 pi. Then we substitute the limit, we will get the final answer, which is Q equals to 9595.765 kg meter squared per second squared.
Introduction of Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let R be the region bounded by C. When the vector field is denoted by fxy equals to pxyi plus qxyj is continuously differentiable on an open region with R, then P in terms of x plus Q in terms of y equals to double integral R delta Q minus delta x minus delta P over delta y dA. Or if P is in y terms plus Q in x terms equals to double integral of R delta P over delta x minus delta Q over delta y dA. The application of Green's theorem is in physics to find the two-dimensional flow integrals, in plane geometry to find the area and centroid of plane figures. Green's theorem can only be applied to counterclockwise oriented curves. If integrating a clockwise curve, the sign of result will need to be flipped. Green's theorem question. Calculate the work done on a particle by force field Fxy equals to y plus sine x e to the power of y minus x as the particle traverses circle x squared plus y squared equals to 4 exactly once in the counterclockwise direction, starting and ending at point 2, 0.
For the solution, let C denote the circle and let D be the disk enclosed by C. Then we have to identify the function of P and Q from the equation of the work done on the particle. Then we have the function of P, which is y plus sine x, while the function of Q is exponential power of y minus x. Then we have to differentiate the function of Q with respect to x, which is negative 1, and differentiate the function of P with respect to y, which is 1. Therefore, the derivative of Q with respect to x minus the derivative of P with respect to y equals to negative 2. By Green's theorem, we have to double integrate over the region D, qx minus py dA. Since the disk is circle shape, the dA changed to r dr d theta. So the limit of r is from 0 to 2, while for theta is from 0 to 2 pi. Then we have to double integrate the negative 2 r dr d theta. So the final answer